Hello, everyone, and welcome back to the second talk in the second session. And we have with us Mitesh Khapra. So Mitesh is faculty in the Department of Computer Science and Engineering at IIT Madras, and he's also an associated faculty at the Robert Part Center for Data Science and AI at IITM. And Mitesh has been one of those supermen who has been working in problems that people don't normally address in NLP that Kalika was alluding to. And but recently, he has been working in areas such as deep learning, multimodal, multilingual processing, dialogue systems, and question answering. So before joining IIT Madras, he was a researcher at IBM Research India. And before that, he obtained his PhD from the IIT Bombay. And during his PhD, he looked at reusing resources for multilingual computation. And during his PhD, he was a recipient of the IBM PhD Fellowship and the Microsoft Rising Star Award. And at IIT Madras, he has been the recipient of the Google Faculty Research Award and the IIT Madras Young Faculty Recognition Award in 2019. So, Mitesh, over to you.
Okay, so I'll start. So today my talk is about object detection over scientific plots. This is work done by two of my MS students, Preeta and
Mitesh, we can't see your slides yet. You want to?
Oh, you can't see it yet? Okay, I already shared it earlier. It means, oops. You can hear me clearly?
Yes, yes.
Okay, can you see the screen now?
Yes, we can. Thank you.
Okay. Yeah. So yeah, this is work done by two of my MS students, Preeta and Mitesh, and I'm presenting on their behalf. So I'll just get into the talk straight away. So we all see a lot of plots around us, right? At least in the COVID world, not a single day goes by when we don't see a plot about healthcare systems or number of COVID cases and so on, right? And these plots are there in newspaper articles, they are in research articles, they are in various financial reports, newspapers, and so on. And now what we are interested in is we are interested in dealing with these plots, and I'll just directly jump to the problem statement, which is once we have these plots, we are interested in extracting the objects that are present in these plots, right? So what are the objects in a plot? So all of these labels that you see, right? So you have the legend label which says years, you have the date on the x-axis which says 2004 and the other dates also, of course. And then you have the bars, or you have the legend names like Bulgaria, which tells you the country to which a particular bar belongs. And then you have the actual bars and also the white tick labels and so on. So these are all the different objects which exist in a scientific plot, and we're interested in detecting them. So why are we interested in detecting them? So that once you're given this plot, so in a newspaper, you'll only have the plot, right? You won't have this accompanying table that you see here. And what we want to do is once we have this plot, which is like, I would call it as unstructured, right? It's not in any good machine readable format. We want to extract the structured information from it. In other words, create this table from it. And once we have this table, then we could have downstream question answering tasks as the few examples that I've shown. Here is to be able to extract these visual and textual from the plot. And once you have that, you have all the structured information that is being captured in the plot. Right? So that's the main goal of this work. And so now this talk actually has two parts, right? And I'm only going to talk about the first part. So what we do in this talk is try to answer two questions. The first question is that if I'm talking about detecting objects in a plot, right? And object detection is a well-studied literature. So why is it that I can't use any of those existing methods, right? You would have heard of things like faster RCNN, YOLO, SSD, and so on. So why not use any of those things for this task itself? Right? So that's the first part that I want to analyze why I can't use any of these existing methods, right? So it's a literature survey plus a review, and with actual experiments and trying to benchmark the performance of these models. And the second part of the talk is where we actually propose a model which is better than all the existing models in the sense that it's faster and it's also more performance-wise it's better. But that's the part that I'll not be able to cover today, right? And unfortunately for the second part, I need the first part, so I can't directly jump to the second part. But the first part in itself is interesting and deserves a presentation of its own because it involves some analysis of existing models. And based on those insights, we were able to build a new model, right? So I want to give some thought to those insights that we derived from existing models, right? So that's what I'm going to focus on today. And I would start with why are natural images different from scientific plots, right? So this is a typical natural image in the context of which a lot of object detection work has been done. That means you will be able to put a bounding box around this cat and say that this is the region where the cat is present, right? And now the difference between natural images and scientific plots is that in natural images, you only have visual elements, right? But whereas in a scientific plot, you of course have visual elements like the bars and the legend boxes, right? The square which indicates the legend color. But you also have a lot of textual elements because you have these titles, you have the x-axis labels, the y-axis labels, and so on, the legend names, right? So you have not only have visual elements which you detect in a natural image, you have the additional challenge of also detecting textual elements. The second is to do with the aspect ratio of objects that you find, or the sizes of objects that you find in natural images. So in natural images, you would find what I would call as small or medium-sized or large-sized objects. But the aspect ratio is much more varied in the case of plots, right? Because you could have these very, very small boxes or small objects like this 0, which is at the origin, which is the exact y-axis tick label, right? And we need to detect that. At the same time, we also need to detect this very long box. Right? It's a very different aspect ratio as compared to what you typically see in natural images. And then there might be some medium-sized boxes also, and different sizes and aspect ratios throughout the image. Right? So there's more variety in the sizes and aspect ratios as compared to what you typically see in a natural image. Right? The third difference is more structural information in a scientific plot as compared to a natural image. And the emphasis here is on the word more. I'm not saying that natural images don't have structural information. Of course, when you see a cat, you would expect, say, it to be sitting somewhere or lying somewhere. So you expect that relation that whenever there's a cat, there is something underneath it. Maybe it could be a rug, it could be grass, or it could be a sofa or a chair. Right? So that kind of structural information does exist, but it is much more in the case of scientific plots, because the moment you see a legend box, which is the colored square here, you expect a legend name to be adjacent to it, right? Similarly, whenever you see a Y tick, whenever you see a tick on the Y-axis, you would expect a bar or some artifact to be present in the same vertical space as this Y tick label, right? So there is more structural information or structural relationship present in scientific plots as compared to natural images, right? And the last very crucial difference, right, and which is the center of this talk actually, right? That's where most of the existing methods fail. So how do you do accuracy computation in natural images, right? So what I've shown here, the red box is actually the ground truth box, which a human has labeled. And according to the human, this is the box in which the cat exists, right? And the cyan colored box that you see is the one which is predicted by a machine. And you can see that if you compute the IOU, which is intersection over union, right? So what part of these boxes is common as divided by the total area of the two boxes, right? That's what intersection over union means. And for scientific plots, the accepted convention is that even if there's a 50% overlap in the IOU, or even if the IOU is 50%, then I would mark the prediction as correct, right? Now, let's see what is the ramification of that for a scientific plot. So the boxes that I've shown you here, the red box and the cyan box on the scientific plot, this is my attempt to discover the bar which lies in that region, right? And now these two bars have a 50% overlap. Now, if I were to do the same thing that I do in the case of natural images, and if I were to mark my prediction as correct, sorry, the prediction is red in this case, then I would make a serious error, right? Because if I detect that as the bar, then I would read off its value as something close to 590 as compared to something around 650, as is the case for the true bar, right? So such localization error of 50%, which is acceptable in the case of natural images, is definitely not acceptable for scientific plots. Even a higher IOU of 75% sometimes is not acceptable, and you have to really go for very high IOUs of the order of 90%, right? Now this looks like an acceptable detection, and it has a significant overlap with the true box. And there might be still a 10% error, but I could at least have a margin for that. And I can definitely not tolerate a 50% IOU or a 75% IOU. Right? So this is one key difference. And turns out that most object detection methods, right, they have never been evaluated in this extreme setup where you need a very, very high localization accuracy in addition to the classification accuracy, right? So that's the main point that we want to make through this talk. So definitely, object detection over scientific plots has additional challenges, as I enumerated here. So now I come to the first goal, which is to investigate whether existing object detection methods are adequate for this task or not, right? So we'll take a data set containing plots, and we'll pass it through different object detection methods, and I have listed the most prominent ones here, right? So object detection is a vast body of literature, but these are the main methods there, right? And a lot of variants of these are proposed for specific use cases. But if I were to look at the key ideas, then all the key ideas are contained in these 6 models that I have listed here, or at least most of the key ideas are contained there. And these 6 models, I will be talking a bit more about them, can be divided into 2 main categories, something known as 2-stage detectors and something known as 1-stage detector, right? So we want to evaluate all of these models. There are 2 broad families, 1-stage and 2-stage, and within these 2 families, there are again some subfamilies, and we have taken the most representative models from each of these families, right? So that's the first task that we want to do. So before I go to the evaluation results, let me just spend, say, 5 minutes on telling you what 2-stage and 1-stage detectors are, and what are the most important ideas that have come out in object detection in the past few years, right? So I'll just spend some 5-10 minutes on that. So here's a quick summary. So this is how a 2-stage detector operates. So you have an image, and the first stage is to propose regions on this image, right? So this is where you say that I think all these boxes that I'm proposing, these are boxes that contain objects. Now you go and figure out whether they actually contain objects, and if so, whether the box needs to be adjusted so that the object is properly contained inside the box, right? So the first stage is to come up with these region proposals. And the simplest way of doing this would be to just say take these kind of rectangles or squares or different boxes of different aspect ratios and size and slide them throughout the image, right? Just keep sliding them throughout the image, and every crop that you get, you say, I think there is a object here. Please go and check whether there's an object here, right? So you could do what is a brute force method of looking at multiple such regions in the image, each region corresponding to a different size box and a box with a different aspect ratio. And once you have that, you could crop out that part of the box, okay, or crop out that part of the image. This is a region that I have proposed. And then you want a classifier to do 2 things, or you want a model to do 2 things. One is, tell me what is the object, if at all, contained in that image, right? So here it could be any of the K classes that you're interested in, or it could be the none class, which means that whatever region you had proposed does not contain any object, right? The other task that you're interested in doing is that these region proposals are coming from a brute force method, so they are not likely to be very accurate in terms of completely containing the object. So even in this region proposal here, you can see that the horse is not entirely contained in it. So you might want to make adjustments to the width and height as well as the origin, right? This is the origin of the image or the cropped image, so that once you adjust these 4 values, which is the XY coordinate of the origin and the width and the height, the box perfectly contains the object that you are interested in, right? So you need to solve a classification problem as well as a regression problem, right? So that's what a 2-stage detector does. It has first a region proposal stage, which is brute force or some heuristic based method, and or it could also be a network actually. And the second stage is where you do this classification and regression. And for doing this, so now this is your input, and your output is one of the K classes or one of the regression coordinates. And you could use any model in between. And the most popular model, of course, is a convolutional neural network based model, right? So this is the typical architecture of a 2-stage detector. And now if I were to talk about the main ideas that have come out in 2-stage detectors, then the first most important idea is the idea of something known as ROI pool, right? Where ROI stands for region of interest. And it comes from a very simple requirement that when you're proposing boxes here or when you're proposing regions in the original image, a quick check, are you able to see the mouse that I'm using?
Yes, Mitesh, we can.
Okay, yeah. So this box that I have proposed, I could have proposed boxes of different sizes, right? I could have proposed a squarish box or a rectangle, a small rectangle, a big rectangle, or so on. But once I've proposed all these boxes, the final classifier that I have, for it, the inputs should be of all the same size, right? Because my classifier is nothing but a function which takes in an input x and gives me an output y, and that output y tells me the class to which the input belongs, right? So if this is a function, then all the inputs that this function expects better be of the same size, right? But I have a problem to begin with. The boxes that I'm proposing are not of the same size. Some of them are squares, some are rectangles, small, big, all of this is possible, right? So one important challenge that I need to solve is that the boxes which are of different shapes and sizes, I need to convert them to a fixed length vector here, right? That's the first problem that I need to solve. And the method used for that is something known as ROI pooling. So what it does is it takes the box that you have proposed and it divides it into a k cross k grid, and then does some kind of a pooling in this grid so that the final output that you get is of a fixed size, right? So just as you do max pooling so that the final output is of a reduced size and a fixed size, you could do something like an ROI pooling so that boxes of different sizes finally get mapped to a fixed length vector, right? So this is a very important idea. Otherwise, without that, you cannot have a classifier at the end which expects inputs of the same size, right? So this was proposed very early on in the literature, even in fast RCM, right? The second important idea was to use region proposal networks. So again, I'll not go into the details of what it is, but I'll tell you what it is at an abstract level. So instead of doing this brute force method of trying to propose multiple regions, I could actually have a CNN which is trained to propose regions. And the way it operates it tries to look at different sized boxes in the original image and tell me whether this box is worth considering to be a region which contains a object, right? So it takes this decision even before passing it to the classification and the regression wave, right? So this region proposal network, which is now a model in itself as opposed to a heuristic based algorithm earlier on, was another interesting idea which led to some improvements in object detection, right? And the third idea was that when you use ROI pooling, you're doing some kind of a quantization, right? Because you're doing this pooling operation, which is lossy because you're not looking at all the pixels. In particular, you can look at this white gap here, and hence that's a lossy process. So can I come up with an idea which reduces the loss in pooling, right? And that's exactly the idea in ROI align. Again, I'm not going to the exact details, but the key idea here is that while ROI pooling is a bit lossy, hence it loses some details of the original box, ROI align does something to reduce that loss so that it captures most of the details in the original box, right? So that's the main idea. So these are the three key ideas which have been proposed in the two-stage detector literature. Now, if I were to come to one-stage detector, so they, as the name suggests, don't have an initial region proposal. They have a single end-to-end network. The way they approach this problem is that my original image is just like a k cross k grid. And for every cell in this grid, like this highlighted red cell that I have, I want to make the following decisions, right? And there are quite a few decisions that I need to make, and I'll tell you what each of them means, right? So the first decision is my confidence in whether this cell lies at the center of an object or not, right? So for this particular box, the value of this confidence should be as close to 1 because it indeed lies at the center of this cowboy object, right? Or the cowboy person. The other decision that I need to take is, if this is actually at the center of an object, what are the true coordinates of that object, right? So how much what is the left bottommost point of the actual object? So I need to do that regression problem, just as I was doing in the two-stage detector. Once I have figured out the leftmost coordinate, I also need to know how much should I adjust the width and the height so that the box actually fits the person. And then I have k different classes that I'm interested in. So I need to predict which of those k classes it belongs to. And it would be k plus 1 because I could also predict the none class, right? So all of these different predictions I need to make for this given pixel, for this given grid at this, which has been highlighted. And not just for that grid, I want to make these decisions for all the k cross k cells that I have in my grid, right? So that's how a one-stage detector operates. It tries to divide the image into fixed sized cells, and for every cell, I'm going to make these k plus 4 plus 1 decisions, right? And now the key ideas that were proposed in the one-stage detector literature was, the first one was that, of course, to use this grid, right? This is the idea that was proposed in YOLO, that do away with region proposals. Just think of every cell in the image as a potential region and then make these decisions for that region. The second idea was to use what is known as a featureized pyramid, right? So if you look at the earlier one-stage detectors, they were making their final predictions based only on the last layer, right? And if you are aware of how a convolutional neural network operates, then by the time you reach the last layer, a lot of information gets compressed. So now the problem is, if you had a very small object to begin with, and it will get even more compressed by the time it reaches the last layer, and hence you may not be able to detect any useful information in that final compressed form. So instead of making predictions only from the last layer, why not make predictions from every layer, right? So the idea there is, if you look at the first layer, it will not be compressing the small objects very much. So a lot of information about the small objects may be present in the first layer, and probably the detections for that may be more accurate from the first layer. Whereas if you look at the last layer, then it would come up with a good abstract representation for very big objects, and hence the last layer may be the appropriate layer to look at for classifying or detecting big objects, right? So they came up with this idea of using a featureized pyramid. And the same idea was taken to the next extent by something known as RetinaNet, where they used an entire pyramid of features and then combined these different levels of the pyramid to do the final prediction, right? So these are the main ideas that have been proposed in one-stage detector. And the key thing that matters here is the feature pyramid network, because that is something which is specifically designed for detecting objects of different sizes and aspect ratios by combining these representations learned at the earlier level as well as the later layers, right? Okay. So now coming back to the first goal, which was to investigate these methods. So we did that. So we have created a data set called PlotQA, which has a lot of scientific plots that we have created from real world data. So we have taken data from World Bank, then data.gov.in, then other sources, even from the US government. And all these access variables and labels that you see, they are coming from real world, because they have things like race of students or detection rate of tuberculosis and so on, right? So these are all real world data. And we had collected some 220,000 such scientific plots, which were bar plots, line plots, or dot line plots, right? So all of these three varieties we had. And now the evaluation metric, coming back to the point which I made earlier, if I'm going to evaluate this as I evaluate for natural images, which is to use a map of 0.5, then I'm going to make these horrible mistakes, and I'm going to allow the red box to be marked as correct, which is clearly wrong, because I'm going to read off the wrong values if I use this bar instead of the original bar, right? So we want to evaluate our models at a much higher IOU of 0.75 or 0.9, right? Even at 0.75, this example is of 0.79, but even at an IOU of 0.75, you make reasonable mistakes. So you need much tighter evaluation at an IOU of 0.9. So what that means is that I'm going to mark a predicted box as correct only if it has a 90% overlap with the ground truth box, okay? And I can vary this IOU from 0.5 to 0.75 to 0.9. Sorry?
So Mitesh, I mean, so since we had this network issues, if you could wind up in the next 30 seconds or so, so we can have a couple of questions or something.
Okay, sure.
Yeah.
So then we evaluated, okay, so let me just then maybe just go to the final results that I want to show, right? Okay, so these are the main results that I want to focus on. So all this highlighted L, inverse L that you see here, these are all the existing evaluation matrix, existing object detection methods. And all of them, I'm trying to map their performance to two criteria. One is the map, which is on the x-axis, and the other is the inference time, which is on the y-axis, which lie in this zone here, which is they have a very high performance, which is on the x-axis, and a very low latency, which is very low inference time on the y-axis. But you can look at all these methods, existing methods, which I have highlighted in this L-shaped box. All of them don't lie in this favorable region. The method that we proposed, which combined the best ideas from the one-stage and two-stage object detection method literature, which was to use a feature pyramid network and to use ROI align and to use the backbone of faster RCNN, gave much better results. It's coming towards the favorable zone, but we are still not there, right? We still need to go in this preferred region. And to get there, we proposed a new network. I did not anyways plan to go into the details of this, but we proposed a new network and a new loss function. I'll just quickly mention about the loss function. So most existing loss functions, what happens is once your network reaches an IOU of 0.8, the loss becomes very negligible, right? And that's not something that we want. We want the network to work harder. We want it to be penalized, even if it's doing, say, even if it's producing boxes which have an IOU of 0.9 with the ground truth box, right? Even such boxes we want to penalize. And hence we came up with a loss function which kind of exaggerates the loss even when you have a low, even if when you have a high IOU. That means your network is already producing good boxes which have a 90% overlap, but we don't let the network rest. We still penalize it, and it has to work harder to get even a better IOU, right? So these are the two main innovations that we did. And after that, we were able to reach this preferred zone that we wanted to aim for, where we have a network which has a much higher accuracy, 93% as compared to any of the existing methods, and a much lower latency, right? 23 milliseconds per image, as compared to even the single stage detectors, which are known to be fast, but we are much faster than the single stage detectors. So that's the main result that I wanted to show. And you can read the paper for the other details. So in conclusion, we evaluated existing methods and found out that they don't work well for this task. They are either very fast, either very slow and or very poor in performance. And then we proposed a new model with a new loss function, which is both fast and highly accurate. So I'll end here.
Okay. So thank you, Mitesh. That was a great talk. And it's really, sorry about all the network problems that we had. So I'll quickly ask one question that has been upvoted the most. So can you give us a little bit of insights on what are the downstream tasks that you are thinking of once you do this object detection on scientific plots?
Yeah. So there are a couple of things that we are thinking of, right? So which perhaps goes back to the my initial slide, which was question answering over scientific plots, right? So this project is basically about reasoning over scientific plots. So the main application that we were looking at, right, is that you're given a plot and then you're asked certain questions on this plot. So go really back. So this is like, you would think of it as a spatial case of visual question answering, where instead of asking questions on natural images like where is the cat sitting, or what is underneath the cat, or say what is the color of the coat and so on, you are interested in asking more structured questions like what is the difference between the number of neonatal deaths in Bulgaria and Cuba in the year 2004, right? And so we have built an end-to-end pipeline for this. And the key observation there was that when we replace the existing object detection networks, which don't perform well for this task, and which means the table that we'll get will not be very good, with our object detection network, which results in a much better table with more accurate values here, we get much better accuracy or performance for the question answering task.
So thank you again, Mitesh. There are a lot of very interesting questions in the question panel. If you have time, if you can stay back, you could take a look at those and answer those.
Oh, these are the questions. Okay. Yeah, I'll stay back for a while and try to answer some of them.
Thank you very much. So over to you, Raj.
Yeah, so thank you, Mitesh. Everyone, we'll be back in another in a couple of minutes with the next talk. Thank you for staying here. We'll see you soon.